Hey guys, welcome back to another video. In this video, we're going to be talking about electric potential. Previously, we talked about electric potential energy, which actually talked about the total energy needed for any charge, any amount of charge to come from infinity to a defined point r near a specific charge. Okay, so in this case, we are going to talk about electric potential. In this case, we are going to talk about only one unit charge. So you're talking about 1 coulomb of charge. In all of the cases when you're going to work with electric potential, that is going to give you the value of energy needed to bring an unit charge from infinity to a defined point. All right. So from that, you can already understand that you can derive electric potential from the EPE, electric potential energy formula, by just dividing that entire value, that entire work done value by the charge. And that will give you actually the electric potential. It's as simple as that. The amount of energy required, let's say amount of work done for any charge, any amount of charge divided by that charge, that any amount of charge. And you're going to get the work done for only 1 coulomb of charge. Okay, so I'm going to talk about that. I just gave a heads up. Okay, so what is electric potential again? It is simply work done per unit charge. Very simple. You just divide your total work done divided by the charge, the amount of charge on which the work was done. Okay, so mind you, this electric potential can also be described by voltage V, since by formula, work done, voltage is energy per unit charge. So similarly, in this case, we can apply that as well, and we're going to see the direct application of this. Remember, we mentioned somewhere that right, electric field strength can be described as volt per meter. Yeah, so we're coming close to that. Why we can you can write the unit as volt per meter. So first of all, from this definition, you can already understand that electric potential, which is work done per unit charge, is actually also the voltage, which is also the same definition, work done per unit charge. The only difference over here is for electric potential, you're considering the charge to travel from infinity to a defined point. Okay, so let's see the written form of it and try to remember the definition, since these few definitions, electric potential energy and electric potential, comes quite often in your QBs, right? So the definition for electric potential is the work done per unit positive charge. This is important because they want everything from the point of view of a positive charge, right? So the work done per unit positive charge in bringing a small test charge from infinity to a defined point. Great, that is your electric potential. Okay, deriving the formula for electric potential, I already told you how to do it. We just divide the entire energy, which is electric potential energy for any charge, and divide that amount of energy by the amount of charge for which you figured out the electric potential energy. So very simple, you divide the electric potential energy by the charge for which you figured out the electric potential energy. Great. So if you're moving this charge Q2 from infinity to R, you're going to deal with this charge only. So what was the formula for EPE? The formula was KQ1 times Q2 divided by R, separation. And now you're going to divide this entire thing by Q2 because we want the energy for only one unit charge. So you're going to divide this entire thing by Q2 to get the energy per unit charge. Good. So if you do that, you're going to see that the final answer that you get for electric potential is actually KQ1 by R. And this entire thing, mind you, can be expressed as voltage, or you can just say it's electric potential. But both are the same thing. Great. So this is your formula for electric potential. You can remember it, or just remember the main electric potential energy formula and just remember divided by the charge and you get electric potential. Okay. So, by the way, a lot of people ask that why is electric potential needed when you have electric potential energy? So, having the electric potential, it streamlines everything. What do I mean by that? If you know the electric potential for any field, so here, this is the electric potential for Q1. Now, knowing that, if you know the electric potential of Q1, be it any charge, Q2, Q3, Q4, does not matter. Whatever you bring in this field, you just multiply the electric potential with Q1, Q2 or Q3. So let's put in the numbers. If let's say Q2 was 5 coulomb, Q3 was 10 coulomb, Q4 was 15 coulomb. You know now from the electric potential that if you just multiply this entire thing with either 10, 5 or 15, you can find the electric potential energy at any point. And that is why electric potential is actually quite useful. And there are obviously other use cases as well. And we're going to look into it. So yeah, that was electric potential. And now you're going to work with, again, a similar thing, which is change in electric potential. The logic is pretty much the same. You divide the change in electric potential energy with the charge, the test charge, Q2. Okay, so what was the change in electric potential energy? It was KQ1 Q2 times 1 by R1 minus 1 by R2. That was your change in electric potential energy. So what's going to be the change in electric potential? Simply divide that value, divide that expression with Q2, because you want to know with respect to 1 unit of charge. So if you do that, you're going to get your final answer, KQ1 times 1 by R1 minus 1 by R2. Great. So that is how you find the change in electric potential. You just omit the Q2, right? If you omit it, you're going to get the expression for change in electric potential. All right. Okay, great. So if you want to plot the VR curve, which is voltage with respect to radius, from this equation, if you notice, V is inversely proportional to radius, right? If V is inversely proportional to radius, you get a asymptotic curve like this. It's very it's very simple compared to again electric field strength, which was E is proportional to 1 by R square. This would again be more steep. If I draw it, it's going to be something like this, right? So that is the only difference between with proportional to inverse of R or proportional to inverse of R square. Okay, so this is the curve for voltage and R, or call it electric potential and R. It's the same thing. Why is it the same thing? Because by definition, electric potential talks about work done per unit charge, and voltage is also this exact same definition, which is work done per unit charge. Okay, so we're going to look into next how to derive electric field strength equation from electric potential equation. This part, and none of these are actually in your syllabus, in the sense that you don't need to derive any of those. If you remember the formula, you're good to go. But I'm still going through all the derivations and reasonings just so that you understand every bit of the formula. And similarly, right now, what I'm going to talk about, it's not exactly in your syllabus, the reasoning. If you remember it, that's good for you. But I'm try to understand why if you integrate this variable, you're going to get this other variable. So try to understand this as I go through the entire thing. Right. So the first thing you need to understand and remember that when we integrated, remember the force and radius curve. Force and radius graph. You got the electric potential energy. If I draw it, right. So from infinity to this point, let's say R1, if you integrated it, the force and radius curve, you got what? You got the electric potential energy. The work done to bring it from infinity to a defined point. Good. Similarly, notice that if we integrate electric field strength, we get electric potential directly. How? Notice that electric field strength is nothing but the force per unit charge. So Fe per unit charge. And if you integrated Fe, what did you get? Electric potential energy, right? And what is electric potential, by the way? The electric potential energy per unit charge. The amount of energy needed per unit charge. So you're actually dividing EPE by Q2, by the charge. In both sides of the equation, if you integrate it, it's basically talking about per unit charge. And this entire thing, mind you, is force per unit charge is actually electric field strength. It is electric field strength, force per unit charge. And if you integrate this, you're going to get electric potential, which is work done per unit charge, EP, right? So basically both are the same thing. So if you integrate electric field strength, you're supposed to get, and you do get, electric potential. Why do you get it? Because both are the same thing. It's just in terms of, it's just per unit charge. It is electric field strength is still the force, but only per unit charge. And electric potential is still work done, but per unit charge. So both sides are divided by the charge, the test charge. And that is why if you integrate electric field strength, you're supposed to get the electric potential. Good. So if you understand that concept, why it's supposed to happen, you can now derive the electric potential directly from electric field strength. Okay, right. It is simply that electric field strength is still force but per unit charge. Similarly, electric potential is electric potential energy but per unit charge. So you're actually dealing with the same variable but per unit charge. We're still dealing with force, we're still dealing with work done, but both in terms of 1 unit of charge. Okay, so to go from electric field strength to electric potential, what we saw over here was you have to integrate it. You integrate the force, and you get the energy. So you integrate electric field strength to get electric potential. Remember, both are per unit charge. That's the only difference. Okay, so if you integrate the field strength to get potential energy, how do you get back to electric field strength from the potential energy? So what is the reverse operation? If EFS, you integrate it and get electric potential, what is the reverse of operation? Differentiation, exactly. So if you differentiate electric potential, what you're supposed to get is electric field strength. That is what you're supposed to get. Good. So if you understand that concept right now, we can move on with the derivation. Okay, so to get electric field strength from potential energy, what you do is, what did I write over here? Right. So to get electric field strength from electric potential, you simply differentiate electric potential, which is the reverse operation of integration. Great. So from the previous equation of electric potential, what is the equation? Electric potential or volt the voltage is equals to KQ1 divided by R. Now, how to differentiate? You simply differentiate the voltage with respect to R, What is the value? Oh, by the way, both of these are constants. KQ1 is a constant. So both sides you differentiate with respect to what? With respect to R. Why? Because R is the only variable over here. So you differentiate with respect to R on both sides of the equation. None of these are important for you. You just need to know that this is the equation you need to know for analyzing the graphs. But I'm just going over the differentiation. Anyways, so if you differentiate voltage with respect to R, you get dV by dR. And if you differentiate this side, what you get is, if you differentiate 1 by R, it's going to be, right? So it's going to be minus 1 by R squared, right? Yeah. So it's going to be minus 1 by R squared. So dV by dR is minus KQ1 divided by R squared. Now, does this remind you of something? It should, because it is electric field strength. So see, if you do differentiate electric potential, you get back to electric field strength, right? So on the right hand side, we have the electric field strength, which is equals to dV by dR. Now this is the interesting part. This is what you need to focus on, and is directly in your syllabus, and you need to use in your question papers, right? So from this derivation, what we finally get is that the electric field strength is actually equal to dV by dR. What does that mean? So if you, let's say, have a curve which is explaining the electric potential, let's say EP and R, or let's say voltage with respect to R, that means, so let's say we have two charges over here, one charge over here, and we're going to see how its electric potential is varying. Okay, so inside the charge, I'm going to cover this later on, I guess. Right, I covered this later on. Okay, so let's forget about inside the charge, but near the charge, the electric potential is maximum, right? Near the charge, the electric potential is maximum, and as you go away from the charge, the electric potential decreases, right? The electric potential decreases. So we've drawn, notice, a graph of the potential, the voltage, and R, the distance from the charge. Okay, don't get confused by the term voltage, because it is basically still work done per unit charge. That's why we call it voltage. There's no other reason. So that's why we can call this voltage. So don't get confused by the term voltage and electric potential. Why we're calling it voltage? Because by definition, both are the same, and we can use it similarly as well. Okay. Plus, later on, we're going to learn about capacitors, and there you're going to see how this equation directly applies to find out the the electric field strength between the capacitors, between the charged plates, right? And in that case, the voltage is also found out the same way. Okay, so coming back to this curve, very simply, near the charge, the electric potential is maximum, of course, because it's near the charge. As you move away from the charge, its field strength decreases, so its electric potential decreases as well. Now again, we have drawn the potential by distance curve. Now from here, what they're telling you is to get the electric field strength, this part of the equation, electric field strength, what you basically do is you find the dV by dr, the gradient. Let's say we want to find out the electric field strength of this charge at this position A. How do you do that? You find the gradient. So you find the gradient at this point, at that point, to find out your electric field strength. And you multiply that with -1. You multiply it with -1 to get minus dV by dr to get your electric field strength. So this is why you need to use this formula, because often you'll have the electric potential times distance curve, separation curve, and you need to, in that case, find out what is the electric field strength at this position or this position. And how do you do that? As I just showed, you have to find the gradient, and that is the main purpose of this part, why we differentiated and found this out, right? That is the use case of it. Okay, so in summary, the negative gradient of an electric potential and distance curve will give you the electric field strength. Good. Oh, I did draw this over here. Okay. So you find the gradient, and that's going to be your electric field strength. Okay. About this later on, as I said, there's going to be cases where you need to directly apply this formula to find the electric field strength. Okay, that is in case of, let's say, two charged plates, right? In case of two charged plates, it's going to be different, and in case of spherical or point charges, the interaction is different, and we're going to look into that in details later on. Okay. So the other thing we need to understand over here is about both electric potential and the electric field strength. Right, so in case of electric potential, notice, if I draw a positive charge, over here, and a negative charge right beside it, what do you assume that the field direction is going to be? Out of the positive charge, right? Notice the red arrows. Out of the positive charge and towards the negative charge. Great. Now, if you remember the electric potential and distance curve, your values are going to be plotted on a curve. It's similar to an exponential curve where the values are exponentially decreasing. Great. So in this case, what's happening is, if you draw, let's say at this point, the voltage or the electric potential is maximum. That is near your charge, near your positive or negative charge, near the charge maximum voltage. And that's what we have noticed, right? Positive 20. If you move away from it, what's going to happen? Initially, it's going to be a steep decrease. The decrease is going to be steep. To get a decrease of 5-fold, you just need to cover this distance, that amount of distance, and you get a decrease in 5-fold. Because remember, this is a sort of an exponential curve. Now, if you want to decrease the volt by another 5-fold, you have to travel a farther distance. You have to travel a longer distance to have the same decrease in volt. That is what we are explaining and showing using these concentric circles. I'll explain what that is. So using these circles, what I'm trying to explain to you guys is, notice, to have the same decrease in volt, you have to move further away from the charge. From 10 to 5 again, if you want to have the same decrease in 5-fold, you have to travel an even longer distance. Why? Because at these points, the gradients, the field strength has decreased substantially, right? So that is why, to have the same change in voltage, you have to travel a further distance, right? Okay. So that is the main purpose of showing all this. Similar to the positive charge, if you look for, by the way, concentric circle, what is that? Concentric circle is basically, it has the same distance. For example, this part of the circle has the same distance to the center. This part of the circle has the same distance to the center. This part of the circle has the same distance to the circle. And these circles abide by it as well. From this position to this position, same distance all throughout. And the gap between these preceding circles are equal. Okay, the other thing is, on any concentric circle that is equal radius all throughout, you're going to have the same volt. You're going to have the same electric potential on any point of the same circle. That is, if you're talking about this circle nearest to the charge, they have a charge of 20 volts, and any point on this charge, any point on this circle, you're going to have the same 20 volt, even if it is here, here, or here, right? So that is the point of saying concentric circle, and they have the same voltage all throughout the circle. So if you jump from this circle to this circle, the voltage changes, but otherwise, if you stay in the same circle, the voltage remains the same as long as the distance to the center of the charge is the same. Okay, but however, even if I do say that, you're going to encounter different charges with different magnitudes interacting. And in that case, you may notice that there are different types of concentric circles. Yeah, like this. So over here, what you have is, these are concentric circles as well. These are concentric circles as well. So I'll mark one. This entire thing is equipotential. I mean, these are not concentric circles. Sorry. These are not concentric circles, but these are equipotential lines, right? That is why I wanted to mention this over here, that if you travel on any point on this line that I highlighted, you're going to have or feel the same potential, the same volt, right? For every same line. So let's say I talk about this line or this line or this line. For every same line, the electric potential is the same. It remains the exact same, right? So if we consider this line, it's going to have half volts all throughout this line, right? So that is the point of drawing these circles, or I mean, whatever you want to call this, a shape. So every point on that shape is going to have the same voltage. In case of simple charges, we can draw concentric circles. We can draw concentric circles to describe the equipotential line. This is an equipotential line. Okay, I don't know why I talked about that for so long, but yeah. For the negative charge, again, the same logic, but the curve is going to be on the negative axis. Now, the easy way to remember that is negative charge, negative curve for electric potential or the voltage. The reason behind that is, notice, oh, by the way, for negative charge, the fields are inwards. You probably already know it. So yeah, why minus? Why is there a minus? Why is it in the minus negative part of the y-axis? Why is it in the negative part of the y-axis? And why are the voltage values all negative? As I said, the simple way to understand is the electric potential is negative, so it should be negative. The charge on it is negative, so the electric potential should be negative. However, if you want to understand the entire reasoning, it is actually that if a positive charge is brought into near the negative charge, what's going to happen is the negative charge is supposed to feel a sort of attraction. It's going to pull the positive charge. In that case, the potential energy, if you remember from the beginning of talking about electric potential, we talk about electric potential is negative, and electric potential energy is also negative in terms of attractive forces. In this case, if you bring a positive charge, they're going to be attracted. They're going to move towards each other, right? So since that's going to happen, we can say the electric potential is actually negative in case of a negative charge, because notice again that the fields are inwards. Why is it inwards? Because it is with respect to a positive charge. If you bring a positive charge, the force is going to be inwards. It's going to attract it. Similarly, if you bring a positive charge, since the force and the field of force is attractive, the electric potential or electric potential energy is negative as well, right? And we explained why when attractive it is negative, why when repulsive it is positive. So the same logic applies over here. And that is why the curve lies on the negative y-axis, right? So these are the two curves. For positive, this on the positive axis, for negative, this on the negative axis. Right. So I guess that's it for electric potential. And now we're going to talk about next electric field strength in uniform fields, right? That is how or where you're going to clearly understand why voltage comes into play. Right. Good. See you in the next video.